Hello, I'm Lukas, and I'm going to present to you our research on reinforcement learning in Markov decision processes, where we focus on finite memory strategies which are applicable with very little prior knowledge about the structure of the MDP. So the setting is as follows. We're given a probabilistic system modeled by a Markov decision process, as you can see down there. But crucially, we do not know the transition probabilities and rewards of this MDP in advance. Instead, we have to learn them during the exploration of the system. So the goal in this setting is normally to maximize some kind of cumulative reward. In our case, we want to maximize the long run average reward, also called mean payoff, which is just defined as a limit of the finite average reward collected for finite prefixes of the runs. So there arise two problems in this setting. The first one is that in the real world, we have only finite resources. So all strategies can only use finite memory. And this had actually often been ignored in previous work in this setting. And secondly, we might only work in entirely unknown systems, which means that our strategies do not know in advance to which successor states an action can lead to. Okay, and in both of these cases, what we want to provide is a near optimal strategy. And yeah, this is what I'm going to present to you in the remaining part of this talk. So first, ignore the second issue of unknown systems and only focus on the finite memory restriction. So in order to give any kind of optimization strategy in an MDP, we have to make one assumption, namely that the MDP is an ncomponent. So as you can see in the example, this means that all states are mutually reachable. So this is necessary because after leaving a maximal ncomponent, optimality of the mean payoff with respect to the mean payoff which would have been possible within that ncomponent, which we've just left, is not possible to guarantee anymore. So we don't really can get around this assumption. And moreover, since we're working towards finite memory strategies, we also have to make a slight technical assumption. So in general, if you want to do reinforcement learning in MDPs, there's like a standard procedure which you do, which is first that you explore MDP for a while by choosing actions uniformly at random and constructing out of this an approximation of the transition probabilities and rewards. And afterwards, you exploit this knowledge by computing an expectation optimal strategy for the approximated MDP and employing this strategy. The problem with such an approach is that the exploration can fail to approximate the MDP correctly, which then results in a very bad average reward in the second phase. So instead, what our strategy does is that it regularly forgets all collected information and instead reapproximates the MDP with another exploration phase. This means that the strategy cycles through episodes of exploration and exploitation, and in each of those episodes, it has a high probability of a good average reward. So in the long run, this implies that the strategy actually achieves a near optimal mean payoff almost surely. That's what's written in the theorem down there. Crucially, because we want to have a finite memory strategy, we can't just keep on piling up new information all along. So we have to forget the collected information to make space for the new approximation in the next exploration phase. So the forgetting here is really fundamental. Okay, so this is a way we can do optimization in regular MDPs. But it might also be the case that we do not know for each action of the MDP to which possible successor states it can lead. So in the example here on the slide, we see that apart from the normal transitions of the MDP, we now also see dash transitions, which we call mate transitions. And these are simply transitions from which we do not know whether they exist in the actual MDP or not. So we call Markov decision processes with this property modal MDPs. Now, if we want to try to optimize the mean payoff in such modal MDPs, we directly run into a problem, namely that we can't compute the maximal ncomponents anymore. But as I said earlier, we can only be optimal respect to the mean payoff within a single ncomponent. So the question is, where should we optimize instead? And we propose two solutions for that. The first one is that we optimize in the ncomponent where the strategy ends up in. So this means that during exploration of the system, we might skip a few promising components. But in the end, if we stay in some ncomponent forever, then we want to ensure that we are at least near optimal within that n component. And the other choice is that we might be conservative and we do not want to leave the maximal n component of the starting state, but then we want to be at least optimal among other strategies, not leaving that component. So in order to provide very efficient strategies for these two use cases, we introduce in our paper a new type of n component in modal MDPs. So the first notion is that of possible n components, which is a set of states which can form an n component for some transition function of the MDP. So as you can see in the left example on the bottom here, if the mate transition from Q0 to Q1 exists, and the mate transition from Q2 to Q0 to Q3 does not exist, then all these orange states actually form an n component. So this is exactly the n component for which you have already seen before. So these orange states form a possible n component. There's also a second notion of safe n components, which just means that's a set of states which can almost surely return to the starting state Q0 of the modal MDP, independent of the transition function. So you can see in the right example here that state Q1 can always return to Q0 via action A. So that's a safe n component. And now the great thing is if we take the finite memory strategy from before and employ it in these new types of n components, we get exactly the strategy which we searched for. So if we apply it in the possible n components, what we get is our strategy is almost surely near optimal, but now only conditioned on the case that we stay in an n component forever. And then we're also only near optimal within the n component where we stay forever. On the other hand, if we apply the strategy in the safe n components, what we get is that our strategy is almost surely near optimal, but now only among other strategies not leaving the maximal n component of Q0. Okay, so that's these two theorems on the slide. So to conclude, what we managed to provide in our research is the first finite memory strategy for reinforcement learning in MDPs, which achieves a near optimal mean payoff almost surely. And we also managed to extend this to modal MDPs, meaning that our strategies can also be applied if we have very little prior knowledge about the structure of the system. In order to make them better applicable, it will be necessary to provide shorter phase lengths for the exploration and exploitation phases of our strategies, and to also see on large examples how they actually perform in practice. So we hope that this research helps in future to devise more efficient strategies for mean payoff optimization in MDPs. So that's it from me. Thank you for listening.